This is our IV characterization setup. We've got two lamps here. This one's a little bit larger, a bit more powerful. It has a larger spot size is what I mean by that. So it also has a nice shutter which protects your eyes, but you can see this one's pretty intense. This one's nice. The light comes from the top down. So if you need a probe on the back of your cell and on the front, this is nice because you can get a probe here on the bottom and the top. With some more modern cells like IBC cells, it's better to use a lamp where the light source comes from the bottom, and that's what we have here. So this one, since the light comes from the bottom, you would place your cell face down, and then put the probes on the back for all back contacted or IBC cells, and that's just so that it's easier for you to move the probes, and your cell still gets all the light. So those are our lamps. We have two options. With each of these, you can control the lamp current. In this case, the lamp voltage, which that affects the current, and you can use that to sort of calibrate the cell. This is our Keithley. It's our current meter, our current voltage source meter, and it's connected to the computer. What we would do is we'd sweep voltage across this, and it would give us the current. So you can see a live display of this, but the computer also takes in the information. We've got a nice program that'll sweep the voltage and the current, and then if you just hit solar cell, it'll calculate everything for you, so it makes your life very easy. But calculating those things isn't that hard. It could just be tedious if you have a lot of devices to measure. So we have a reference cell. This is a cell with a known current and efficiency. So really all we need is the current, the short circuit current. So it comes with a sheet that we use to keep it calibrated. And so the cell just has a certain voltage, a certain current, the short circuit current density, fill factor, maximum current, maximum voltage, maximum power, and efficiency. It also tells us the device area at the top, and it gives us an IV curve so you can sort of see what to expect. So why do you need that? Because these lamps can kind of drift over time, the voltage can change as they degrade, the current intensity could drop. You're going to want to make sure that you're accurate so that whatever data you're reporting isn't going to be far off. So the reference cell is just a really stable solar cell. You'll notice it wasn't very efficient. It's only about 4% efficient. But it's useful to have so that you can make sure your data isn't totally bogus. So I'm going to sort of line this up over the lamp here. We're just going to use the down-facing lamp just to make our lives a little easier. So we don't have to get probes. I'm going to hit so this thing has a nice little negative terminal, positive terminal, and we're just going to use alligator clips to connect to the negative and positive on the Keithley. So we're using the right side, that's the input output. If you have 4-terminal method, you would just put it on the other two sides as well. So now in the software we can tell it what voltage to start and end at. I've just kind of got it preset up for negative 250 to 600. If you recall, I said the voltage can reach like 700 millivolts, but the cell isn't that great, so 600 is really all as far as you need to go. You can also tell it sort of how many points you want, so how fast it will measure, and the compliance current. If there's a certain current you don't want it to go past if you don't want to damage your cell. And lastly, you need to change this to 2-point. We're using a 2-point method, not 4-point method. And then it's easy. You can just hit execute. You'll see this begins to sweep voltage, and it'll monitor the current as it sweeps voltage of the cell. It's a pretty quick scan. Usually don't want to scan it for too long. What's nice about this software is a lot of softwares can take the measurement, but only a few of them actually calculate all this stuff for you. So if we enter our device area, which is on the sheet, 0.479, we can hit solar cell, and it'll just automatically calculate the efficiency, fill factor, VOC, JSC, Vmax. So one of the things we should do for the assignment is to calculate all these values manually by hand, and then try to see how close you get to the given values, just to see if you understand the theory. Be careful with negative values, again, where it's negative current in the raw data. but obviously your power is not going to be negative. So just correct for that. And what you do. So we're a little bit off. The lamp's not perfect, but we're just going to consider it okay because it's a little hard to tweak this one. The ISC of this curve is 5.3 milliamps. We should be getting a current of 4.6 milliamps, so it's a little bit high. But the efficiency is a little bit lower, which could be due to how we're probing it.
Which current is that?
The maximum current. Sorry, hold on. I got them mixed up. ISC is 5.3 milliamps, and the ISC should be 5.4. So the ISC is low. That means our lamp intensity isn't that great. But that's okay. We're just going to save it for now. Just consider it calibrated for your assignment. So I'm going to save the data. There's a notepad. So in the file I sent everyone, it's going to have efficiency, fill factor, all those parameters already calculated, but you need to take this data and calculate it for yourself. You don't need time, you don't need the 2-point probe status. You just need current and voltage, and you should be able to calculate all of those things. Again, assuming your incident power is 100 milliwatts per centimeter squared. So we'll save that. Reference cell. So now what we're going to do is measure an actual cell. So first I'm going to disconnect the reference cell. Put that somewhere safe. Now we knew the area of our reference cell from the sheet. You can see that even though it looks like it's big, it's just this small circular area in the center. We're going to measure a larger area IBC cell. The problem is the size of the cell is larger than the size of our lamp spot. So we need to determine the radius or the diameter of this hole. That's basically sort of your mask, which I believe is about 4.8 centimeters. We'll just assume that's the case. I have a ruler on there. So on the back of this IBC cell, this one's kind of damaged. You can see just a bunch of white lines. These are actually copper-coated lines. And on one side, you'll see pluses, and on the other side, you'll see nothing. So that's our positive side, and that's our negative side. The front of the cell doesn't have any contacts at all. Again, it's an IBC cell, but you can see I've got some damage to the cell. So it may not perform as well as we hope.
Why is it blue?
The blue color comes from the silicon nitride passivation coating. Kind of as the thickness of the silicon nitride changes, it'll change the color of the cell. But blue is a pretty common color for most cells. So I placed it there. I've sort of centered it as best I could based on I drew some lines beforehand. We have what we have here. We have a 4-point probe set up here. So each of these probes has two tiny little fingers on them, and that's to help reduce some of that lead resistance that we're going to encounter. And you'll notice each probe has two wires coming out. So for the one on the positive end,
We have
so I'll put the positive end on both the two positive ones. Again, they're in the same place, but we're going to set it up for the 4-wire sense method. Then I can place my probe on the center terminal. And then for our negative probe, which is over here, plug it in first. It doesn't matter which order these go in, because again, they should be the same. But just keep, black with the black and the red with the red. And then we'll put that on our cell there. So I've already sort of pre-set the height so that these probes are pushing down and making good contact with the cell. That's important. If you have poor contact, you may not get a diode curve, you might just get noise.
Why is there 4?
So if you just do a two-terminal measurement, there's resistance added from the leads.
Oh,
and if you're trying to get below 1 ohm, that
so
can
this one excludes the contact resistance?
Yeah, you lose the contact resistance, you lose lead resistance, and you should see a lower series resistance as a result. So you'll get a sharper VOC slope. And that's standard practice to do that. They even argue about how closely probes should be spaced. They do like a multi-probe measurement at NREL. So we're just going to change this back to 4-point. So the sense mode is now 4-point, so it knows to use both wires and not just the two we were using before. We're going to execute again. So we see the curve's a little bit bigger this time. That's good. That means we're getting more light. One issue, if we do something stupid and we just hit solar cell, you'll notice the efficiency says it's 176% efficient. That doesn't make sense, right? Now, does anyone think they can guess why that is?
Area.
The area, yeah. We left the area with the size of the old one. This is actually much larger. We're using the whole area of the light instead of just a small device area here. So if we set that to the correct area, it was like 4.8 or 4.9, and hit solar cell again, you get a much more reasonable efficiency of 17%, so that's pretty good. Again, anything over, if you ever get a cell over 26-77%, you should save that file and call NREL or something. Start writing your paper. Yeah, we can see the cell's much better than the reference cell, but it's already cracked, so it's not as it's a little more fragile. It's harder to keep safe. But it's a 17% efficient cell, fill factor of 70, much lower voltage of 535. That's kind of strange. I think that could be because we're only providing light to one part of the cell and not the entire area. So there's some places where it's shaded and current flow is reduced. And yeah. You'll notice so ROC is actually our slope at the VOC, and it's below 1 ohm, so that's good. Our 4-terminal setup has helped. We're below 1 ohm series resistance. Our shunt's pretty bad. It's possible that this cell's damaged. We really should have much more shunt resistance.
How do you calculate the series of the shunt?
It's the slope of these lines at the ISC and the VOC.
At the intersection.
So our ROC is the slope at the VOC.
Isn't that always going to be like 90 degrees this way?
So V equals IR, right? You have V and I at each of these points, and you can calculate R from that. And just take the slope to get that.
Okay.
Yeah. It's the only equations you'll need are P equals IV and V equals IR, and you should be able to calculate all the things that it gives you. And again, assume your light intensity is 100 milliwatts per centimeter squared. It'll show up in all the files. Yeah. We can go over the messing it up. So we're done with this. When we're done, always make sure you turn your lamp off. You don't want to leave these running. As you let them run, the lamp hours build up and the lamp degrades. You eventually have to buy a new, very expensive lamp. But yeah, that's it. I'll clean up later. We'll talk about the QSS CD method. You can pause it for now. Anyone else want to film? I can. You can film again if you don't mind.
Yeah, it's fine.
Okay. So this is our QSS PCD setup. Again, as before, there's a flash lamp up on the top, and this will flash light, and then the sample will sit on this surface here. It's got a heater in it to keep it at a constant 25 degrees Celsius. And then beneath this is a coil in the very center, and that coil will capture the eddy currents from the electrons that get excited from the lamp flash. And then it'll measure how quickly those electrons sort of settle back down and recombine. The longer that takes, that's the lifetime. In the top here, there's also a little photo detector just to keep it calibrated in case this thing pulses sort of inconsistently. So this one's also pretty well automated. I've already got a file set up for this cell. Here you can sort of see what it gathers for you. So on the left here is blue is your light intensity. So that's sort of how the light flashed. There's a big flash, a big pulse, and then it settles back down. And then in the red is the photoconductance of the sample. So that's how long the electrons stay excited inside the device. Using this, it calculates your lifetime. So depending on where you pick to do this, you can pick your MCD. That's sort of depending on your light intensity. and it'll fit the inverse lifetime there. So for this cell, the lifetime's about 3,000 milliseconds, or sorry, 3 milliseconds, 3,000 microseconds. This is pretty good. It gives a VOC of 717 millivolts, which is pretty high, and a fill factor, implied fill factor of 84. So since there's no contacts on this device, it doesn't actually measure the VOC or the fill factor, it measures the implied one. So based on, if you made a perfect device after this, that's would be what you'd get. It also can measure resistivity, a few other things. If you have surface texturing, you may need to adjust some settings or other issues. The device we're going to test today is a textured sample. No, it's not that one. It's too small. So this is our device. I've already broken up a piece of it here. Oh, first, before we test, we need to zero the device. So that just, if there's any contamination there, it kind of becomes aware of it. So I'm going to clean this off. It's kind of dirty. Sorry. It's been sitting here a while. Okay. And we'll just re-zero it one more time to make sure it's accurate. You guys don't have to do anything with this one. We're just showing you how it works. Probably don't need to zero it then. So just take my sample. I'll line it up with the ring so it's centered. Again, an edge is missing, but that should be okay. And then we'll just hit measure wafer. The light's going to flash, and it'll measure the response. So maybe you want to get the lamp process. Yeah, we'll hit measure. And it's just disconnected. Something went wrong with our battery. Sorry about that. Wait a second for it to restart. This should be good.
What's the advantage of the flash compared to a continuous light?
I'm not sure why it's not working. That's not good. Something messed up. So maybe we can't demo this right now. It's saying it's providing enough voltage, but this never happens. Sorry, guys. So we'll just cancel that. But basically, it'll show you all the data we just talked about. The lamp will flash, and then pretty quickly it'll give you the lifetime. And so that's QSSPCD.
I have a question.
Yeah.
What's the advantage of the flash compared to continuous light?
So this can also do a transient measurement. It can stay on, which is better for certain structures. I can't remember exactly what type. There's typically, most people just use the generalized measurement type, which is the QSSPCD type. You can do transient, but I think there's some reasons why you shouldn't do it. Sometimes it exaggerates voltages, but it's useful for certain devices. With the continuous, so this is measuring the lifetime of the current, right? So if you just left the lamp on, you would never see this drop. They would just continue to get excited, right?
What if the time period of the flash is more than the period lifetime?
That can happen. It tries to keep it short, like less than 10.
It just did.
What? It's broken. Sorry, guys. Let's see if I can get it one more time. There we go. So that's the flash. Kind of hurts your eyes if you stare at it, but and it'll calculate your lifetime. So yeah, your VOC lifetime is still pretty consistent from the last time we measured it. We can also try the transient method. So note that at 716 millivolts, at about 3,000 milliseconds, if we change this to transient, it's a much longer measurement. And then we can hit measure again. I don't know, see, I don't think I've got it quite set up for this on my sample. You can zoom the, you can also dilate the lamp pulse time in the photoconductor as well. Okay. So yeah, this sample is really not good for this. It's not calculating VOC at all, but it is giving us pretty similar lifetime. You can see our photoconductance doesn't look right at all. But yeah, I don't typically use the transient mode. So yeah, that's about it for this guy. Put this away really quick so I don't break it. Stop filming for now. It's definitely broken. I gotta unplug it. So that's that. Last thing we'll talk about really quickly, we also have a EQE setup. This is pretty similar to measuring IV or measuring your solar cell device, but instead the lamp goes into a spectrometer, sorry, monochromator. So it'll take the incoming white light and split it up into its components. So, you know, red through, or blue through sort of the infrared. And you can give each one of these select wavelengths to the device at a time and measure sort of the current at that light, or the efficiency, whatever you really want to measure. Okay, this is
What if it's still buzzing?
It's unplugged now. I shouldn't. But yeah, this is useful for, again, if you think your cell is not performing well in the blue, usually means your front surface has an issue. If it's not performing well in the red region, usually your rear surface is having trouble. So you could have defects or other contamination, or you just didn't do a good job building the device. We won't run through that because it's not really set up, but yeah, basically you can just sort of chop your light into little pieces and measure the device at each one of those as well. And that should be all of the lab. Any questions?
So what conclusion can you make if it doesn't perform well in a certain wavelength?
Well, you can tell, let's say if your surface texture isn't helping, or maybe you've got some sort of layer on the front that you've deposited that gave you better electrical performance, but it's eating away at your current. You can determine things like that. Again, if the back of the cell is bad, it's usually the red which will be affected, because red will penetrate further in the device, and the blues will be more absorbed in the surface. So depending on if you see a spectral loss in efficiency at either of those, you can assess which sort of layer is being affected. It's not perfect, but it's one way of doing it.
The longer the wavelengths go, the deeper it penetrates.
Yeah, red has more of it.
Yeah. So you can use that to kind of help you figure out what's going on. Also, usually you plot it in what's called an EQE spectra, and instead of having low efficiency, they're usually near like 100%. So people like those because it makes the cell look better. But yeah, that should be it.